Hello everyone. In the previous hybridization video, we discussed a few examples starting from beryllium chloride, boron trifluoride, ammonia, and iodine pentafluoride. And one thing that I forgot to do in the last video is actually tell you what the hybridization for iodine pentafluoride is. Hopefully you were able to figure it out, but let me just circle these so I can show you. So it'll be S, and there's 3 P's and 2 D's. So it's going to be S, P3, D2. That's the hybridization for IF5. And then also, I was discussing how you come up with the structure of the compound. And I said that none of what we had done actually tells us that there's lone pairs on the fluorines, but I just wanted to show you that these pairs right here are actually each of the 3 pairs on each of the fluorines. So if you were to draw all of these boxes over again, you would have 5 sets of them, and it would show you the lone pairs on each of the fluorines. So actually with this method, you can draw the entire structure without even knowing how a structure is drawn. You can deduce it all from there. So I just wanted to go over a few more examples just to really solidify this topic. And the 2 examples that I want to discuss are very similarly drawn: xenon difluoride and then xenon tetrafluoride. So you might wonder, first of all, xenon, since it's a noble gas, you're wondering why it's doing chemistry. Usually the noble gases are very inert and don't do any chemistry, but it's after the d orbitals, so it actually has access to a d orbital. Let's draw the electron configuration so we can actually see that. Starting from krypton, because I don't want to write out the whole electron configuration. From krypton, it's going to be 5s2, 5p6, and then it also has access to the 5d orbital, but there's zero electrons in it. So since it has access to the 5d orbital, it can actually do chemistry because it could bump its electrons up into it. So let's draw the orbital box diagram so we can see that. There's going to be 9 different boxes now. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's S. We have the 3 P's and the 5 D's. So originally we have 2 electrons in the S, we fill in our P's this way with the 6 electrons, and we have nothing in the D's. Now in the example of xenon difluoride, that means we have 4 fluorines that bond. So let me draw the box diagram for fluorine. Let's start with the electron configuration from helium. So from helium it's 2s2, 2p5. It doesn't have any access to d orbitals or anything else. That's all that's in the second energy level. So we're going to draw that out now. There's going to be 4 boxes. Oh, I drew that horribly. And originally there's 2 electrons here, and then 1, 2, 3, 4, 5. This one's S, P, P, and P. So as we can see, fluorine has an electron that needs to be paired to something, and now we can actually do work with xenon. We can bump one of its electrons up, and let's see what that actually does for us. So when we bump this electron up, it gives us 2 empty spaces. So that means we can make 2 bonds. If we were to bump another one up, we would make 4 bonds. But for right now, let's look at the one where we make 2 bonds. So with this in mind, we can have another fluorine. Let me just rewrite all this quickly. And this is our hybridization with the S, P, P and P. And here's our electron that needs to be bonded with something else. And so now with a different color to show you the bond, since fluorine is more electronegative? Well, now it's debatable because of the noble gas, so let's just look at it as fluorine still being more electronegative and wanting to grab this electron here. It's going to take it and bond there, and this one's going to bond here. So now we have two bonds, and we can see that for xenon is going to be sp3d. And we don't write the 1 as in all of chemistry. We never write any of the 1s that are involved, so it's just sp3d. And that is for xenon difluoride. Now we also have the example of xenon tetrafluoride. So let's see how we can make two different sets of compounds with one element, xenon, by changing the hybridization of it. So let's draw the fluorines again so you can see how we can make 4 bonds with them. And once again, we're going to have 4 boxes, S, P, P, and P. And our 4 boxes down here. Even when you don't have to, always practice drawing using Hund's rule. So we start with S, and then using Hund's rule, we go up, 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 down, and down. So now we see once again there's an empty space. We need to pair. And the problem is here, if we keep xenon with the hybridization that there is now, there's no available way for us to bond anything. We just have pairs, and pairs can't bond with anything. They're happy the way that they are. So with this example, we're going to have to change something. And I did mention it earlier, so hopefully you're catching on. But in order to change this, we're going to have xenon. It still has the same electron configuration, but now we're going to structure things differently. We're going to have the 9 boxes, S, the 3 P's, and the 5 D's. And now instead of having 3 lone pairs and 2 unpaired electrons, we're going to have 2 sets of lone pairs and 4 unpaired electrons. We're not adding or subtracting any electrons, we're just moving things around in order to make more bonds. So we just bumped up one of the lone pairs and turned it into 2 unpaired electrons. So now we have 1, 2, 3, 4 spaces where a bond can be made. And so the way that this is going to happen is we have an electron that bonds with this, an electron that bonds here, an electron that bonds here, and finally here. Now I ignored these bonds for now, that was for our other compound. That was for xenon difluoride, now we're doing xenon tetrafluoride. So now we have the 4 bonds on this side. And that's how we make xenon tetrafluoride, and now we can see that the hybridization actually changed. It's sp3d2. So notice that here we just had 1 D, and here we have access to 2 of the D's. So that's how the hybridization changes, and finally let's just see how the structure changes. So with xenon difluoride, it's going to be 1 xenon with 2 fluorines. And what can we see from the orbital box diagrams? We can see that we have 3 sets of lone pairs because we have 3 boxes with lone pairs inside. So 1, 2, 3, 4, 5, 6. So those are the 6 electrons that come in 3 sets of 2 pairs. And now we have xenon tetrafluoride. So now we're going to have 4 fluorines. I'm not drawing this exactly correct in terms of 3D geometry, but in terms of 2D this is fine. And now we have 2 sets of lone pairs, which you can see right here. And now once again, like I said at the beginning of the video, we can see how many lone pairs are on the fluorine by looking over here. So fluorine has 3 sets of lone pairs. And it'll be the same thing for this structure. Some people draw lines instead of dots, but I know even though that's a little quicker, it's just a little too lazy. We should draw the dots. The line should only be for the bonds. And that's not a double bond, I was just trying to exaggerate the bond. So hopefully seeing these two examples helped you understand how you can have one element bond in different ways. And in fact, you could actually bump up more electrons and have it bond even more ways. So it's really interesting, and if you just play around with different compounds, you could start to see a pattern and understand how to do this yourself. Thank you for watching.